Okay, we are back, and thank you. Very interesting comments in the chat, and people are asking about missing data. Let me answer those a point made by, hope I pronounce your name correctly, Zaifa. Yeah, it's a really good comment that you made. Can we just include them, use the mean? And the answer is don't do that. Why? Because when there's missing data, data is often missing for a reason. And we've so far we talked about error. Someone writes 300 instead of 3, and somebody does not answer it. But usually the truth is when that happens, when it's missing, when the data is missing by randomness, that's called missing completely at random. But think about this. If you have, maybe you really have 18, 19, 20 children, and you're in a residency program. Maybe you just even started residency. And they say, do you have children in the questionnaire? You say yes. If you say, how many children do you have? You just started work last week. Is that the time you want to tell people that you just started residency, but you have 25 children? You would be like, let me skip this question. So you see that data, it misses for a reason. Give children in schools, little children, letters to take to their parents. I can assure you that the ones who take, and again, someone might say, oh, is this sexist? No, I'm just telling you what data looks like. The children who give those letters to their fathers will not come back with those letters the next day signed. But the ones who give those letters to their moms are more likely to have those letters adhered to and signed. So you see that missing data is not missing at random. The prediction of missing data could be dependent on what is happening with the person who you are asking those questions. Okay, so and I was saying there's a very interesting aspect of research that does data imputation. We use very advanced methods to impute data. So I can know whether this person has, I'm just kidding, you can't know, it's just data, and sometimes it's hinky, Anyway, let's go on. So
Before you move
now,
on, sorry.
remember what we said. You run your regression, and you can make mistakes in your categorization. But even after you run your regression, you can't just jump into the streets and say, oh, we have done the regression, so this is the final answer. There's what you call post-estimation. So you see that you've estimated your coefficient. So this is the estimation. Post-estimation, you want to do what people call a quality check, or in statistics we call it regression diagnostics. Are we really correct? Is this the best method to use? And when you are doing this, there are things called assumptions of linear regression. I'm going to show you some funny things, and you'd be like, oh, life is not cut and dry. It's not white or black. There's a lot of gray and a lot of assumptions. So again, sometimes it's a matter of opinion. Regressions are not cut and dry. Statistics is not the truth. It is a framework that we use to come as close to the truth as possible. So, so if someone is telling you something and you've done the regression, don't just assume that you are correct. There are different ways to the truth. So that's a little philosophical. Let's talk about the statistical way we do our QC. Okay, so I told you there are assumptions you make in statistics. Number one is that there is linearity, and don't worry, just be exposed to this. We'll talk about it subsequently. That there's also homoscedasticity. It's a big word. I like it. I should put it on my jersey. That there is normality of your error terms. That your errors are independent from one observation to the other. And then there are issues of multicollinearity, and you have to specify your model correctly. And there are also outliers, leverage, and influence. And we'll talk about this. But before we talk about that, let us come back to something we saw in lesson 5. Probably when you were doing lesson 5, you were like, I don't know what this is, and why do they think they should take some time to discuss this? A lot of the things, and again, props to Dr. Abioye, a lot of the things that are in the slides are carried forward, lecture by lecture. So don't forget the stuff you learned in the past. They are always carried forward. So remember when we draw our regression line, if we switch to 5, remember when we said you have a line of best fit. Should we do it? Do we have time? Let's try. Let's try. Show you something real quick. Oh, this is where it comes from. Okay, you see it here. There it is. I just borrowed it. Okay, look at this, right? So this is our data. And then you do a regression. Is this your line of best fit? Or is this your line of best fit? Or look at this one. Is this your line of best fit? Or is this your line of best fit? Now, let's imagine that what you have in red is your line of best fit. Remember that we said that you cannot assume that everybody must fall on this line. So look, for example, at somebody with SPP at week 24 of 100. At week 24 of 100. So you are telling me that this is the line, the best fit should be around 130. But look at all these people with 100. Look at this person here, 100. This person here, 100. This person here, around 100, 100. This person here, 100. This person here, 100. Basically, what we're saying is that the difference between where you are in the data and the line of best fit is called your residual. The residual is the difference between where you are in your the data, where an observation is, and the line of best fit. So look at where I am right now. This person here with 120. The residual is the distance between 120 and the line here. And so let's call this 110. So this person's residual is 10. This person's residual is 5. This person's residual is maybe minus 5. This person's residual is minus 10. This person's residual is, what is this? About minus 60. Okay, I'm sure we get it. Let's go back to where we are and continue talking about, the assumptions. Okay, first assumption. Okay, linearity. So this just means that, remember that we're talking about line of best fit. What if this thing is really not a line? What if it's a curve? What if the relationship is a curve? Can anyone tell me what relationships may be curves? Income, for example. When you're a student, you don't have any money, and then as you get older, you finish school, you get a good job, you get a promotion, you change jobs, your money is going and then you get to retirement and your money starts to go down, or your money plateaus. So and that's a bad example, right? But not all relationships between predictors and outcomes are straight lines. So you can't regression everything. Or you can regression everything, but you have to bend it. That's, again, remember, it's about assumptions. You have to bend your model, and we'll talk about bending your model just now. Okay, so what if your relationship is not linear? What some people do, and it's highlighted in yellow, and Dr. Abioye, feel free to jump in here. Some people will introduce another term. They would find the square of their X value and add it into the model. What that does is typically it straightens the relationship. You see, this is kind of, I don't know, Nigerians call it route to the answer, but the answer will get to the answer. And some of you might say, oh, this is nonsense. But we know that these things are robust to truth as far as statistics is concerned. Some people will find the square root. One of my professors has a chart that tells you what to do depending on what your data looks like. If it's bending upwards, if it's bending upwards, the way it's bending in this thing, you find the square root. So it will bend it downwards more, it will become a little straight. If it's bending downwards, you find the square, it will bend upwards. So you see, you're manipulating your data, and that's why someone earlier said manipulator, but that was the wrong answer. But maybe he was being he was prophesying, I don't know. But anyway, that's what you do to make sure that your relationship can assume straightness. But there's something else you do, is after you've done your regression, you are going to look at what they call the residuals. We just talked about the residuals, and then you draw a graph of your residuals on the y-axis and your predictor variable. So your predictor variable might be number of children of blood pressure on the x-axis, and you do what they call a lowest plot, a lowest line. And what you expect is that lowest line will be straight and at 0. But I told you I'm going to show you some funny things. You see, this is not exactly at 0, and it's definitely not straight. You see, but in statistics, if you saw a lowest line like this, you say, well, see, it's not at 1. This place is not at 1. It's at -1. It's around 0. So we're going to assume that the condition of linearity has been met. Remember, these are assumptions. Within the assumption of linearity, we are going to assume again that this thing is linear. Okay, so you can call it the answer, but I'm telling you that these things are robust to truth. They are robust to truth. But again, somebody might say, come on, man, what are you talking about? This thing is not at 0. Okay, so let me show you this one. You see this one here? When you do your residuals so these people use predicted values. You can use predicted values, or you can use your x, this is predicted values of y actually, or you can use predicted values of x, or you can use your x. I think you can use your x, and you're going to see it's either way. You can use predicted values of y. I don't know if we've talked about predicted values of y, but let's not go.
We kind of have when we talk about predictions.
You can see this one looks kind of straight, and why is it bent at the edges? It's bent at the edges because at the edges your data is more variable, and someone will say even in the middle this thing is curved. Let's be honest. But again, this is just how this is assumptions within the assumption. So this has met your assumption of linearity. This has met your assumption of linearity. If it does not meet your assumption of linearity, you come back here and you change or adjust your model. If it's bending upward, you square your x. If it's bending downwards, you square root, or you find the cube root of your x, or you find the log of your x. Someone is going to ask me, what if someone will ask, what if it does not work? Well, you are on your own.
Hey, boy.
Okay, so
hey, boy,
let's move to homoscedasticity. Okay, Dr. Romakinde, if you don't mind, you're on the hot seat.
Hello. Hello.
Let's bring you on.
Hello.
And unmute yourself. What is going on?
Hello.
Can you see a pattern here?
Okay, I can.
You're muted. So I can see that you're talking, but you're muted.
We can hear him. It's your voice is low. I don't know. We've been trying to say that in the chat, but we can hear the doctor speaking.
Yeah, can you hear me now, sir?
I can hear you.
Okay.
The whole time I thought it was my fault. All right.
Okay. So can I have the question again now?
Okay. Oh, I'm so sorry. Hold on one second. Are you guys saying that you've not been hearing me since I've been talking?
We heard you, okay, but you couldn't hear us when we were speaking back.
Oh, okay, good. So sorry about that. Okay. So did anybody say anything important that bears repeating?
No, I think one of the key things was that people were complaining that your voice was far from your mic. And so there was some strain to hear.
Okay.
I heard okay, but maybe because my mic volume my speaker volume is loud.
Okay. Okay. I apologize. I forgot to wear this thing, and so that's why. Okay. I saw the chat blowing up, but I was like, maybe people are asking questions. Oh my God, I'm so sorry, people. Okay, let's go on. If there's anything that you need clarification with, let me know. But I was asking Dr. Romakinde and saying that, can you see a pattern here?
I can see the chart.
You can see this, but is there a pattern? Is the data maybe moving up, moving down, or is it just randomly dispersed?
It appears random.
Right. What of this one?
It's also random, kind of.
Okay, but can you see that this data is fanning out? The top is going like this. The bottom is going like this. So if you are this person, you are more likely to be low. Yes? Yeah. You can see it, yes, right? Sir. Great.
Yes, sir.
Nice. This thing that you are seeing where data fans out is called heteroscedasticity. Excuse me. It is a violation of the assumption of linear regressions. So let's come back here. So remember, we talked about linearity. You plot your residuals against your predicted Y, or you plot it against your you plot it against an X, and you expect that your lowest line will be straight. And I've told you that this thing is straight. It's an alternative fact, but it is straight, no matter how you are seeing it. Okay, when you do the same thing, you also look for homoscedasticity. You can see that here, and two things that you should see. Number one is that if you draw a line from 0, what is above 0 should look like what is below 0. So if you fold this graph at 0, it will be a mirror image. Again, that's you are just using your eyeball to say that. You are not saying exactly it must be, but you can assume, because there's no pattern here. So one, it should be distributed around 0, but 2, if you fold them, they should be a mirror image of each other. But let's come here. You can see that it's distributed around 0, yes. But I mean, when you fold them, they are a kind of mirror image, but they are not random. If you are here, for example, if you are in this area of this fitted value, you are likely to be closer to 0. But if you are in this level of X, you are likely to be further from 0. So the distance, your value of X, is actually a predictor of how close you are to 0. So therefore, but you don't see that here. Whether you are -1, whether you are 0, whether you are +1, your distance from 0 is likely to be the same. When there's a fanning out, or when there's a fanning in any direction, can be a fanning in, it is heteroscedastic. You want your residual plot to be homoscedastic. Otherwise, you have violated that assumption. And so what you do is you come back here and you manipulate your data, not in a bad way, but you manipulate it to meet your assumptions. Okay, let's move to the third one. Normality of residuals. This one is really funny because what we're saying is that when you, I'm not going to go into details because I don't even know if I understand it myself, but what you expect is that those residuals are normally distributed. And I can show you using paper and biro what it means for your residuals to be normally distributed, but we don't really have time because we still have to go into linear regressions. But you do what they call a GG or PP plot. You expect that your data will fall along this diagonal. And again, you might say it's not falling, but I'm telling you for a fact that it's falling. Again, it is not 100% that you must be on the line. And I borrowed this from Dr. Abioye, you know, and I think that this falls on the line. This is a straight, This is a correct QQ plot. And so somebody might say, come on, man, you're just giving examples for everything. But imagine that this line started from here and ended up here. That's going to be very different from what you're seeing here. So this is not bad. This is not bad either. Okay, let's quickly talk about, so you can see we're breezing through because we need to talk about multiple regression. Let's talk about outliers and leverage. So we talked about residuals. If the distance between an observation and the line of fit is very great, look at this one here. This is huge, but this is small. This value is called an outlier. That's the definition of an outlier. So even if this point was, but what is now the definition of leverage is if your value of X, so this would be your, this Y will be your predicted outcomes, or this would, not your predicted outcomes, this would be your Y, because now you just want the data. And this, would that be your predicted Y? I don't know. No, it can't be a predicted Y. A predicted Y is a straight line. Anywho, any data observation that has a huge distance from your line of fit is called an outlier. How huge? Some people will say, I don't know, if you use your eyeball, you can see this is huge, but this is small. But when you're looking at your x-axis, that's your predictor axis, any really extreme value of X can be called as having high leverage. It's a high extreme value of X. So this is, somebody might say this is an outlier on the x-axis, and I would say, yes, you are correct, but it is not really an outlier because the distance to the line of fit is slow. But what is an influential point? An influential point, you might think that outliers will be influential, but not necessarily. An influential point is any outlier or high leverage point that shifts the line of best fit. So if you had a line of best fit that after you remove this outlier, let's say your line of best fit becomes like this. I should have put a line here. But if it becomes like this, just because you dropped your this outlier or this leverage point, then you would say that that point is influential. Now, the question is, should we drop outliers? Should we drop high leverage points? Should we drop influential points? Personally, I don't think so. If your data is correct, you are modeling for a population, and those outliers are part of the population. We don't kill people because they are billionaires, although people say it's the rich, I don't know. But those people are outliers. But if you're modeling for society, I don't know if you should remove them because they are part of the population you are modeling for. Okay, let's quickly talk about model specification. We're going to jump something here because we're going to talk about it in multivariable. I'm going to try to do this in 3 minutes, and we have 20 solid minutes for multivariable. Okay, so now, look, remember what we had done. We looked at hours worked predicted by number of children, but we ran two models. We ran one model continuous, we ran one model categorical. In fact, we ran one model with a false categorical, then we ran one model with indicators. So we're going to assume indicators and categorical will kind of give you the same thing. I believe it should give you the same thing, but you know, very close to each other. So which model should you use? It's usually a case of opinion, right? Sometimes the software you are using will determine, you know, which would you choose and why? I have an answer for this. And remember, if you attended some of my past lectures, including last week, I tell you that research is for decision making. So if I was looking at BMI, people love to code BMI as continuous. They love it. For every 1 unit in increase in BMI, your risk of cardiac disease increases by so and so. Wow, excellent. But what does that mean to the patient? If you tell a patient for every 1 unit increase, like, doctor, I don't know what you're saying. So personally, depending on the situation, I would use categorical for BMI. I would say, sir, madam, if you move from being normal BMI to overweight, or if you move from overweight to obese, your risk of death will increase by so and so %. Or I would say, if you lose weight and you move from being obese to normal, you would reduce your risk of death by half. That patient understands what you are saying, and that patient can go and make the decision. But if you say for every 1 unit increase, you're just making yourself happy. You've done statistics, but your patient or the governor of your state who you are asking to build more gyms or more exercise grounds would not understand you. So again, it's a matter of opinion, but you have to think about the end user. Who is using this research, or are you just using it so that you can write a dissertation? It's really up to you. Okay, so sorry, I was going to ask people that question, but because of time, we're going to move quickly. Okay, now, but there is another answer, the one that provides the most information using the smallest number of variables, the one that is least complex. Remember, I told you I'm kind of lazy. I just use that categorical. It's very easy. It's very straightforward. If you use a full model with 5 variables, you can call it a full model. If you use a smaller model that you've removed a few things, you can call it a parsimonious model. Okay, another thing in model specification is sometimes you leave out variables that are important in the model. Remember when I told you guys about coffee and bladder cancer, and they ran regressions on coffee predicting bladder cancer, and they found an effect, but when they forgot or they left out smoking, and that is confounding. It really was the smoking that was leading to bladder cancer. Sometimes you just throw in stuff. So remember when we said you should use your common sense. So students will come to me and say, I want to understand what causes people to die in a hospital after surgery for heart disease. I say, okay, great. They'll say, so what should I include in my model? I say, what do you know about heart disease and surgery? You can't just include anything. You should know maybe the age of the person, maybe the sex of the person, maybe whether there's an infection of the wound. It is your subject matter expertise that will come, that will predict this. I'm not going to go into this now because it's going to come up in a further slide. Okay, so you've seen that you can't just go regression in. You have to meet assumptions of linearity, homoscedasticity, normality of the errors with your QQ plot, but you also have to make sure your model makes sense to you and you're a subject matter expert. And we missed something else. Yes, and you have to either account for, sometimes your outliers are outliers because somebody wrote 300 instead of 30. So you want to drop that observation. Other times, you know that there are people who are walking around the streets of Lagos and Freetown who have a blood sugar of 500 or more. That's not an outlier. That's just a ticking time bomb. Should you remove them from your model? I personally, it's a matter of assumption, opinion. I don't think you should. Okay, so we did it. 20 minutes. Let's